Hello everyone, my name is Abhiraj Chouhan. I am a student of MTech-IT fourth semester. Today I am solving the question paper of internal third of numerical analysis and design for my assignment. So let's start. Let's start with question number one. Question number one asks us to write an algorithm to solve a system of simultaneous linear algebraic equation using Gaussian elimination method. Gaussian elimination method is a direct method that transforms a system AX is equals to B into an upper triangular system which can then be solved by back substitution. The algorithm starts with the augmented matrix A B where A is an n by n into n coefficient matrix, and then B is the n by 1 vector of constants. The first phase is forward elimination for each pivot position k from 1 to n minus 1. We eliminate the elements below the pivot a k by subtracting multiple of rows from rows k from the rows below it. Especially for each row I from k plus 1 to n, we compute multiplier m is equals to a I K A by A K K. Then update row I as row I minus M into row now K, adjusting both A and B. This process creates an upper triangular matrix. Second phase is back substitution. Starting from the last equation, xn is equals to bn by a n n. We solve each xi from I is equals to n minus 1 down to 1 using xi. The algorithm assumes that no pivot is zero, otherwise pivoting is needed, which we will discuss in the next question. Or of Due to the nested loops in the elimination phase, making it efficient for small to medium size, this method has complexity systems. Here you can see the algorithm we have written for this question. Now let's move to the next question. In question number two, we need to explain pivoting in solving simultaneous linear algebraic equation and why it is needed. Pivoting is a technique used during Gaussian elimination to improve numerical stability and avoid division by zero. In Gaussian elimination, we divide the pivot element AKK by at each step. If AKK is zero, the algorithm fails because division by zero is undefined. Even if the pivot is non-zero but very small, dividing it by it can amplify rounding errors in floating point arithmetic, leading to inaccurate solution. This is special this is especially problematic in systems where coefficients may widely in magnitude. Pivoting addresses this, and by selecting a larger pivot element, partial pivoting, the most common approach involves searching for the largest element in absolute value in the current column K from row K to n. If the largest element is in row R, we swap rows K and R before proceeding with elimination. This ensures pivot is as large as possible, reducing the multiplier magnitude and minimizing error propagation. For full pivoting goes further by swapping both rows and columns to use the largest element in the submatrix, but it is more complex and less commonly used. Pivoting is crucial for robustness, especially in real-world applications like circuit analysis or structure engineering, where matrices can be poorly scaled. I have included an example in my slide showing how small pivot leads to error and pivoting fixes it. Does So now let's move to the next question. Question number three. Question number three asks us to explain what ill-conditioned simultaneous linear algebraic equations are and how to solve them by refining the Gaussian elimination method. A system is ill-conditioned if a small change in coefficient or constant result in a large change in solution. The indicators of ill-conditioned statements are it is a high condition number nearly a singular matrix. The problem caused by ill-conditioned systems is numerical instability, inaccurate solution due to the floating point precision limitation. The solution for this is refining Gauss elimination. Now moving to our next question, question number four. Question number 4 asks us to write an algorithm to solve simultaneous linear algebraic equation using the Gauss-Seidel iterative method. Unlike Gauss elimination, Gauss-Seidel is an iterative method, making it suitable for large sparse systems which direct methods are computationally expensive. The algorithm starts with the system Ax is equals to b, where A is an n by n matrix, b is the constant vector, and x is the solution vector. We rewrite each equation to isolate which ensures convergence. Starting with an initial guess x0, often the zero vector, the algorithm iterates as follows. The kth iteration for each I from 1 to n. Compute, notice that we use the newly computed values x j to the power k plus 1 for j smaller than I immediately, which distinguish Gauss-Seidel from Jacobi method and often leads to faster convergence. The iteration continues change until the change between successive iteration is below a tolerance or maximum number of iteration is reached. The complexity per iteration is O n to the power 2, but the method excels for square system. The Gauss-Seidel is widely used in applications like solving partial differential equations such as in heat transfer simulation. My slides includes the convergence example also. To wrap up, we have covered essential techniques for solving systems of linear equations. Today we explored the Gaussian elimination algorithm, a reliable direct method, and discussed importance of pivoting to ensure numerical instability. We have examined ill-conditioned statement, learning how iterative refinement can improve solution in such cases. Finally, we developed an algorithm for the Gauss-Seidel iterative method, a powerful approach for large sparse systems. I hope my explanation provided a clear understanding of these techniques. Thank you for watching the video.